Okay, so I'm going to try to talk a little bit about the Maxwell-Boltzmann distribution, and you can see it's going to get pretty nasty. So let's maybe take a second to review probability distributions, and let's do that really quick. So probability distribution density functions, we can debate to no end the distinction. Let's not care about it. Probability density functions for a continuous variable. The probability is always positive. Total probability is 1, meaning this integral is true, or the total area under the curve is 1. The probability of being between 2 points is given by the integral from these 2 points. And then for a small enough interval, you could just use this shortcut result as long as your interval increment size is very small. This is approximately true. And then I'm going to add in one thing that wasn't on the video previously. It's this piece up here in red. Expectation value. So this is going to come up more than once this semester, so you should actually try to understand this, especially because the last couple weeks of class we hammer on this. So all this probability distribution stuff, density function stuff, comes up again in quantum mechanics. So you got to know this stuff, at least to get out of this class, and then you can forget it. All right, so the expectation value of x to some power n is given by, integrate this function, x to the n times the, I should say p of x here. I think we're using p of x. Was it blue? Whatever. So you basically take the probability density function, p of x, and you stick x to the n in there, and this gets you this. Why am I mentioning this? For example, if we use n equals 1, the expectation value of x is a fancy way of saying the average value of x. All right, so if you want to get the average value, which is sometimes written as x with a bar over it, we just say integrate x times the probability distribution function or density function. All right, so that's our probability review. Now let's go and look at the Maxwell-Boltzmann distribution. All right, this is on page 84, volume 3, if you want to follow along. There's an assumption. We're going to assume that the energy is purely translational kinetic. Let's assume monatomic gas so we don't have to think about rotation and all that stuff. Okay, this was the Boltzmann distribution in general. Notice the energy relates. You could imagine there's going to be a 1/2 mv squared here. We'll take a look. Notice there's a 1/2 mv squared. So that's kind of where this is coming from, right? And then this is now going to be a probability density function, so it has to be normalized. In order to be normalized, these weird constants come out. Now, this part is a little bit tricky here, this 4 pi v squared dv. Okay, where does that come from? Well, we're talking about speed instead of velocity, right? You could have a speed entirely in the x direction, or entirely in the y direction, or entirely in the z direction. And so if we convert the velocity components into speed, we're basically taking a 3D integral into a spherical polar integral, right? And so, right, if we assume v is equal to the square root of vx squared plus vy squared plus vz squared, we'd have to do an integral over dvx, dvy, dvz in order to figure this out. And in the end, shortcut, basically you get a 4 pi v squared, just like you get a 4 pi r squared dr when you do the conversion or the Jacobian to spherical polar. Okay, so basically this is from a coordinate transformation, this comes from the energy part, and this here is the normalization, just making sure the entire area under the curve adds up to 1. How do I know this plot looks like this? Let's evaluate the function really quickly. If we plug in 0 for this, e to the 0 is 1, right? However, when you multiply by v over here being 0, that starts at 0. Now, if you go to really large values of v, let's say v is close to infinity, this number would be large, but this would be e to the negative infinity, which is much, much smaller. When you multiply these two together, you basically get 0. So we get 0 at low speeds, 0 at high speeds, and there's going to be some maxima in there. Okay, cool. And I'll show you how to make this plot in Excel in just a minute. Now, if you're wondering where we're getting this square root and the pi in here, right? Maybe it helps to know there's an integral table on page 84, and I would give you an integral table like this for the test. I don't expect you to memorize this garbage. But so you'll see sometimes they're recorded as I subscript 2, meaning square x by this weird function, cube x, or, oh, oops, I forgot the limits on here. It's important to mention this, the integral table has limits, so you don't get to, this isn't going to have a plus c on it because these are definite integrals with limits. Excuse me. But you can see that there's a pi in here and an a, and so when you do all this math, you could imagine that somehow that pi relates to this one. Because when you do this integral, you're going to have a square root of pi to some power here. So notice we get a square root of pi in the basement to some power here. So that makes sense, hopefully. All right. An interesting phenomenon. VMP, that means most probable. Okay. If you have the most probable speed, that's basically the highest point on the curve. Think, how could you get the most probable speed? Pause the video if you want to think about it. 3, 2, 1. Well, I noticed the most probable speed occurs at the maximum. How do I maximize any function? Take a derivative, set it to 0, solve for v. So you can find v most probable using that procedure. Take the derivative of f of v. All right? Now notice when you're taking the derivative, this is a subtle thing. I'm trying to be a stickler here. Here I'm talking about f of v dv. So clearly f of v is just that part. So if you're wondering, wait, how do I take the derivative of dv? You don't have to, right? Where this function relates to this part in the black square. Now, if you want to get the areas under the curve, you need the dv and you need the integral. Okay, v average, as I was mentioning earlier, v average or v bar, as you'll hear it called, v bar is equal to v average. That's just the expectation value of v. So you plug in v, and now this is your new density function. Now, a quick note on the units while we're looking at that. You can see I left the units blank. I like to try and think that through. What do we know about any probability function? I know that the integral of f of v dv is equal to 1 with no units. And that's over all space. In this case, velocity space. All right, so in this case, notice the units of this must be exactly opposite the units of that. Well, velocity has units of meters per second. So this function must have units of seconds per meter. Okay. And notice, when you take this entire thing in black, if that has units of seconds per meter, then you multiply by meters per second, you got no units, that's the probability density. All right, VRMS, that stands for root mean squared. So you square the speed, you take the average of it, that's the expectation value, and then you take the square root of it. So this gives you how you can compute VRMS for these. Notice I3 would be pretty handy for computing this one because you're going to get a v squared times a v, you get a v cubed here. This one has a v squared times a v squared, you get v to the 4th. So you can see why I've got these integral tables listed here. And it's just a real annoying process. You can do problem 19.10 after this video to see if you know what you're doing. And that's on page 85, I think. Yes. So you should do problem 19.10, page 85, immediately following this. Now, before I'm going to show you some tricks on how to make these plots and understand it and see what happens. But I do want to mention one more thing. This was done in 3 dimensions, and I've got a worked example in 3D in problem 19.10 here, a way I might mix this up on exam day is to do this. Is this going the right way? There it is. Whoops. Ah. Oh no! Okay, whatever. Can we see this now? Yes, we can. In 1D, the probability distribution looks like this. In 2D, the probability density function looks like this. You might be saying, dude, this is dumb. How am I ever going to get a 1D gas? What if you had some sort of nanowire, which is basically like a long rod, and you have a gas somehow trapped inside there? 2D, what if you had gas trapped on a surface? So if you had a very thin sheet of metal, the electrons in there behave a little bit like this, and they would obey this kind of distribution function. So these, even though they seem like totally stupid because you're like, gas isn't 3D, or I mean, you're probably thinking gas isn't 1D or 2D, but in certain cases it can be. And so what I'll do on an exam is maybe do exactly the same types of questions, but change the distribution function, which is going to change the integrals a little bit because there's different powers of V in here. So going back to this one here, oh, well, there's the V squared in this one. So notice there's different powers. Okay, come on. All right, so now I'm going to show you how to make these plots just so this makes a little bit more sense to you. Let me do a quick screen share. Oops, share screen 1. All right, and I'm going to make this a little bit bigger here. All right, and so let's just delete this and start over here. Now, I want to point out a couple of things here. I just typed in the mass of a helium, so I'm basically working off page 84. This is the mass of a helium molecule. There's my Boltzmann constant. Here's a temperature. This is one of the coefficients that shows up in there. Let me get my annotations. That constant sitting out front is this. And notice this term right here is that. And let me, okay. So now, and here I will point out, notice there's a big jump here from 220. I've got a bunch of the cells hidden and I can unhide them later. So the graph is going to look a little bit weird when we first make it, but as soon as I unhide these cells, so maybe I'll just do this really quick. You could type in, okay, and so just to show you what I did for this constant, oh, let's just do it from scratch. We'll just delete these and do it over. Okay, so this should equal something raised to the 1.5. Now it's the mass, which is this cell, divided by, let's see, 2 times pi times K Boltzmann times the temperature right there. Whoops, did I forget another? Oh. Yep, I forgot another parenthesis there, so let's not accept that, sorry. Right there. And so if you look up here in the formula bar, it's probably a little bit, even though the font is smaller, it's easier to read than this crowded screen. So I got A2, okay, that should be this. All right, and now this term is equal to the mass divided by 2 times K Boltzmann times T. Oops, that one I will accept. All right, so there we have it. So V, I'll type the first two numbers. You pick a small increment size, and you notice from the plot we're going way out to 4,000. All right, and again, notice between here and here, there's about 100 cells, 200 cells hidden. So let's type in this function now. Whoops. This is equal to this constant, and I better put F4, dollar signs on that. So to get those dollar signs to pop on there like that, I click the cell, I hit F4. All right, that makes it a constant, times EXP of negative this constant, I better make that a constant, times V squared. V squared will be the cell A10. Oops. All right, And I don't know if you could see that cell light up when I type it. A10, that's the right cell, squared. All right. And then this entire thing has got to be multiplied by 4 times pi. And remember, when you're doing pi in Excel, you got to do pi, open paren, close paren, times v squared. What was that? A10, whoops, squared. All right, now I'm going to crank this out. Great. So now I'm going to make this plot. I'm going to insert a scatter plot. And it looks a little bit wonky. That's because I've hidden a bunch of rows. So now I'm going to go in here and unhide the rows. And we see this kind of pretty looking shape. All right. And maybe what I'll do is just make these bigger here, so you can see better. All right. And now we could, I don't know, maybe I'll get rid of the grid lines so you can see better. We should probably add tick marks and all that jazz, but let's just look at the cool part. What happens if you double the temperature? So I'm going to type in 600 here, and when I hit enter, think what should happen to the curve. And maybe what I'll do is I'll make a note, this spot right here, right? This corresponds to V most probable for 300 Kelvin. What do you think is going to happen if the gas gets hot? What should happen to the curve? Will it get taller? Will it get shorter? Will it move to the left? Will it move to the right? Will it become skinnier? Will it become fatter? All right, let's go ahead and run this. I'm going to, remember, I was just changing this. It was at 300, and now I'm going to make it 600. Here we go, enter. Aha, we see the curve gets a little bit shorter, a little bit wider, and we see the most probable moves over. That's V most probable at 600K. Now, if we keep jacking this up, oops, let me get rid of my annotations here. Let's see what happens if we go all the way up to 1,000. This is going to look kind of funny, right? It starts to move way over. Right? And we can see it's shifting way out there. At this point, notice a lot of the graph is missing, so we'd have to go in and change our increment size. So this is one of the challenging things about this. And I should probably mention, C, the speed of light, not sound, the speed of light is an upper limit that we're never going to reach. More on this when we talk about special relativity at the end of the semester. But notice for the temperatures we're talking about, the speeds are like 4.5 times 10 to the 3. We're nowhere close to the speed of light yet. Even if we include the next chunk of the graph, right? We might get up to 10 to the 4th, 10 to the 5th, 10 to the 6th. It turns out, unless you're at speeds close to, say, 1 to 10% of the speed of light, that's when the corrections start to matter. So this is going to be good for a huge range of temperatures. All right.